I want to say a little bit about the normal model. This is the first place that I've found I want to really take issue with Bach, Vellman, and DeVoe. In Chapter 6, they say that when we use the normal model, we assume the distribution of the data is normal. And they correctly say there's no way to check for sure whether this normality assumption is true. This is what I'm reading up here. And it's almost certainly not true. Real data don't behave like mathematical models. Good point. But then they say to use a normal model, it's sufficient to check the following condition. It should be unimodal and symmetric. And that's it. And that's really not, I think there's something really wrong with that. There's a lot of situations where the data is going to come out with the histogram being unimodal and symmetric, and it's importantly different from a normal model. And in particular, there's this very, very useful rule that is absolutely true for a normal model, or something that really follows the normal law, which is the 68, 95, 99.7% rule. That 68% of your data is going to be in a certain range between -1 sigma and 1 sigma. 95% is going to be between -2 sigma and 2 sigma. And 99.7 is going to be between -3 sigma and 3 sigma. So in other words, say the probability that you're going to get, or the proportion of data that you're going to get that's out here past 3 sigma, is half of 0.3%, so 0.15%, if it's normal. So it's really unlikely you're going to get stuff that's significantly further than this kind of bulk of the region. And the fact is, there are distributions that have much, much thicker tails. And I want to show you an example of that. So I put on the calculator two distributions. One is the standard normal distribution. And then the other one is called the Cauchy distribution. I'll write that down. The name is not important. There's plenty of examples like this. But this was just the one with the simplest formula that I wanted to write down. Okay. And I made sure that the Cauchy distribution is going to have a histogram that looks sort of in the middle a lot like the standard normal and has roughly the same width. And in particular, I made sure that the IQR was pretty much the same, or pretty close. So here we go. Here's the normal model, and I'm plotting it from -5 sigma to 5 sigma. This is the standard normal, so it's from -5 to 5. And you notice that the first graph is almost invisible here and here, because there's very little of a tail. Then the next thing that plotted was something that's a little higher peak, a little less on the shoulders, but a significantly bigger tail. If you can see that, we're going to concentrate on the tail in a minute. A really significantly bigger tail. And so I want to show you a cool tool that we haven't seen before in what I've been doing so far, to graphically show these kinds of calculations that we do with a normal model, or any kind of idealized histogram kind of thing like this. And that is to shade in a particular region and find the area under the curve. And it's called the integral in calculus, but we don't have to worry about that. We just have to know that it's this funky symbol, fx dx, whatever that means. It's just second calc 7. And so it's going to tell us up here, it says normal PDF. Okay, that's the normal distribution. And it asks for, and so I don't need to change that. So I won't use an up or down arrow to change which function I'm doing. Lower limit, x equals 0. That sounds good. That's right in the center. Notice that this other distribution is definitely unimodal and symmetric, and qualitatively looks like the normal. But we're going to see that there's some very important differences. Okay, so using this method, it's hard to get exactly 1, but I'm going to go to a little bit more than 1 sigma for the normal, and I'm going to check. Okay, so that's about 36%. It gets, I don't know if you can read it too well, it's 0.356. And if you double that, so about 35.5%, and multiply that by 2, about 71%. And that's expected because I went to 1.06. I didn't go to just 1. Okay, so if I doubled that to get the whole middle region, we're getting 1. Okay, so that's just a check of what we already know. Now I'm going to show you second calc 7. I'm going to press an up arrow, or a down arrow would work, to get to y2. The formula isn't important here, but I happen to know the formula for this other distribution. And I'm just going to go back, lower limit, let's say exactly 0. That's nice. And then I'll go out to the same upper limit, 1.06. And you'll notice it just shades in. It's hardly different, but it shaded in everything under this thing with the top peak. And unfortunately, actually, no, wait a minute. It didn't realize it should unshade something else. Let me try and trick it into doing this over. because it just was confusing. Okay, so we're going to redraw it. There's the normal. Here's the thing with the bigger tails, lower shoulders, but a higher head. Okay, and now we're going to do second calc 7, see if we can get it to it right. We're going to do the other one, lower limit 0, and upper limit just a little bit above 1 because it's hard to get exactly 1. Okay, that's what it really should look like. It's everything under this other distribution. So that's going to be, you should just think of this as a histogram with many, 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 many counts and very small bins. And so it's basically just looking at how much stuff is in the histogram, adding up all the stuff in the bins, and that amounts to taking the area under the curve. And this is about the same. So this is about 32%. So for this one, 2 times 32%, 64%. Okay, roughly the same. Not exactly the same, but roughly the same amount of stuff in the middle. And so it would be about 64% if I shaded both sides out to 1. Okay, so these really are roughly similar in terms of what they have in the middle. The difference is in the tail. And the difference is this 99.7% rule is going to be utterly false. So what I want to do is I want to change the window. I want to start at x equals 3. That's going to be 3 sigma for the normal. And I'm going to go out to 15, which is way far out for the normal. There's nothing out there. That's just ridiculously far out for the normal. But I need to go out that far for the other one. And then y min, everything's going to be pretty small here. So I'm going to have a little bit negative so the axis is not right on the bottom because there's words that appear on the bottom. Let's try that. Okay. So here's the normal. Notice it's just there's very little even at this small y scale. These dots are 1/1000th for the y scale. You hardly see anything. But whoa, this other distribution, even though it looks a fair amount like the normal qualitatively, it's got a much bigger tail. So let's use the second calc 7. Okay, so let's look at the normal PDF. It should, I'm going to have to scoot all the way over. It should give us the 99.7% rule. So 1/2 of that, just the upper tail. So it's 3, 2. I probably don't have to go all the way to the right-hand end. That should be fine. Look at the value here. Y is something times 10 to the minus 10th. That should be enough. There we go. And indeed, I get about 0.0015 roughly. And that's, if you double that, that's the 0.3%. Okay, so 0.15% of all the stuff in the histogram, all the data in your huge table, if they follow a normal distribution, will really be beyond 3 sigma. Very small percentage. The chances are 1 out of 600 that something's going to be in this tail. And 1 out of 300 that it's going to be in either tail from lower than minus 3 sigma or above 3 sigma. So now let's have the contrast though. Second calc 7, I'm going to do up arrow to the other one. Now you can see the little spot is there. And I'm going to go all the way back to x equals 3. Just barely goes off because I wanted the scale to try and show the normal. Okay, now I'm going to go up. And the thing is, I'm not even going to get everything here. This is going to be an underestimate. I'm going to go all the way to the right, but it's going to be an underestimate of this tail because there's definitely more to come. There's more up there. But hopefully we're going to get most of it. And at least it'll be some sort of lower bound for how different these guys are going to be. Look at how much more stuff there is in that. Okay, so 0.055. Okay, so that we're getting, it's 5.5% just in the one tail, and it's greater than that. Double that, you're going to get more than 11% in the two tails. This is compared to 0.3% in the tails for the normal. So if you have this kind of distribution and you think it's normal and you modeled it so that, and then you checked it so that you knew that the middle parts were correct, as I checked it at the start. Yeah, I know I can tell they're a little different, but roughly they're good. The interquartile range is very, very similar. So maybe I can use the normal model. Well, the normal model would, and suppose somebody's going to die if you get some event, some point in this distribution that's beyond 3 sigma. Or at least something else. Somebody gets seriously injured. Here, the person using the normal model says, don't worry, the chances of being in either tail past 3 sigma is 1 out of 300. Okay, that's probably not very good for people dying, but okay, something bad happens, something seriously bad happens. You say, okay, that's too bad, but it's not very likely. If it's really modeled by this distribution, in fact, it's going to happen more than one time out of 10. And so we're not ready at this point in the book to really deal with a lot of different models, but I wanted to warn you that when they just kind of make this implication, unimodal and symmetric means normal, that's utterly false. What they really should be saying is we can't bring in all the possible models right now, and the normal, there's many situations where it's true. And we'll investigate more about when it is true and when it's a good model. But I don't want you to take on faith that anything that's unimodal and symmetric is normal. It's just not so.